Okay, so let's get started. So somebody in their grand wisdom gave geochemists the last word. Uh, and especially after Bruce's lecture yesterday, where he had some negative impressions about ratio plots. So I'll talk to you today about the volatile budgets of the terrestrial planets and some of the challenges we face in trying to understand how the different terrestrial planets, excluding Mercury, acquired their volatiles. So when you look at a image like this with Venus, Earth, and Mars, what do you think is the most volatile-rich planet? Venus. Okay.
Look at that atmosphere.
So everybody agree it's Venus?
No.
No. Okay. Some people say Mars.
I don't think we know.
And Michael says, I don't think we know.
What is volatile?
So that's a great question. So what is volatile? So somebody's volatile may not be another person's volatile. So let me tell you the volatile species that I was going to talk about today. So this is from the periodic table from Bill White's lectures. So I'll talk to you today about what I would call the noble volatiles. These are the rare gases: helium, neon, argon, krypton, xenon. I don't understand why people don't like xenon. There are 9 isotopes of xenon, so you can make 9-dimensional plots. If you want to do ratio plots, any idea how many different ratio plots you can construct? 81 different ratio plots. The good news for you guys is that I'm not going to talk about the xenon isotopes today a lot. And then there are the ignoble volatiles: hydrogen, carbon, nitrogen. Somebody else looking at this might classify them a little bit differently. They may say that these are the volatiles that make sense, and the rare gases are the ones that are like impossible to interpret. Hopefully I'll convince you that may not be the case. So coming back to the question of what's a volatile, so a lot of people would consider potassium to be a volatile element, like Bill. So when you look at a plot like this, again, Bill White shows something similar. So this is the distance in AU against the temperature. This may not be exactly accurate, but it shows higher temperatures in the inner part of the disk, decreasing as you go out. Once you are somewhere between 2 and 4 AU, that's what we would call the snow line. So outside of the snow line, you get ices. Interior of the snow line, you get mostly the metal oxide. So the idea is, in general, the terrestrial planets would be more volatile depleted with respect to these ices, because you don't get a lot of condensation in this region of ices. And the outer planets, Jupiter, Saturn, Uranus, Neptune, those have the major inventory of ices. So this is a paper from a few years ago from Peplowski. This is based on the messenger data, and then also shows where Earth and possibly Venus might lie. So this is the thorium content against the potassium content. This is Mars. The red dots are the messenger data. Oceanic crust on the Earth lies around there. A few data points from Venus. So these are from the Russian Venera missions. There. And basically, this line here refers to a constant potassium to thorium ratio. And the moon is off here. So effectively, one could argue that the 3 terrestrial planets, or the 4 terrestrial planets, Mars, Earth, Venus, and Mercury, have very similar potassium to thorium ratios. So they don't show significant depletions in potassium necessarily. So what about the other volatiles like hydrogen, carbon, nitrogen, noble gases? Do the different terrestrial planets have similar inventories, or do they show differences? Okay, so that's what I'll be focusing on in the lecture today. Okay. And there are some questions about the terrestrial volatiles that I think we can answer. They are pretty straightforward in many respects. So these would be things like, what are the potential volatile sources that could have contributed to these terrestrial planets? What processes could have sculpted the volatile budgets? When could the volatiles have been delivered? So those are questions I think that we can answer. But maybe the questions that we really want to get after are not what are the or what could have been the potential sources, but what are the sources? But to do that, we have to really address this question first. What are the volatile compositions in the budgets? And then we can start talking about what are these volatile sources? What are the actual processes that sculpted the volatile budgets? And where these volatiles actually delivered? Okay. So let's look at the potential volatile sources. And the first one is the solar nebula here. And this is, again, an artist impression showing the protostar in the middle, the nebular gas with embryos and little planetesimals growing in them. And the idea is that if you have embryos that are in this nebula, and if the embryos reach about the size of Mars, they're big enough to actually gravitationally attract these nebular gases. And then if you... Bill? Mike?
I like the picture. I would wish that you could spend just a moment more on it. And two things I would ask of the picture is, when in the accretion history do you think that this is supposed to be imaging in 10 to the x years? And does the gaps for you represent something significant?
The gaps like here? I don't know if the gaps represent anything significant or not. It's possible it does represent something significant because Jupiter might be growing out here and it might be clearing material. What time frame this might be representing, I'm going to address in the next couple of slides. Okay. So again, the idea is if you have embryos that are about the size of Mars, you might be actually gravitationally capturing these gases. And you might then dissolve the nebular gas into the embryos through a magma ocean. There is a second possibility in terms of acquiring the nebular signature, or the solar signature that we call, which is through irradiation of dust. So this is still a nebula that has a fair bit of dust in it, but one of the things you notice is that radiating the dust in the midplane of the nebula is kind of hard, because the opacity is quite high. So if you have to radiate the grains, you have to effectively loft it to the edges of the nebula. And that may be okay because we know based on mass-independent oxygen isotope fractionation that that's where some of the chemistry must have been happening. So again, you might be getting this nebular or solar signal through irradiation of the dust. There is a key difference, though, between the capture of the nebular gas versus the irradiation of the grains. So when you're irradiating the grains, you might impart a slight amount of mass fractionation. And that's because the implantation of the different isotopes are going to be a little bit different. The heavier isotopes will have a higher momentum, and they'll be implanted into the grain deeper. The lighter isotopes would be implanted to shallower depths. And then when grains collide, it's possible that you might be eroding the outer few nanometers of the grain. And that means that you're not going to effectively preserve this solar or nebular signature in the grain. It's going to have a slight amount of mass fractionation. Whereas the nebular gas presumably is going to really tell you what the sun's composition is. So now back to Bill's question about what time frame are we talking about here. And this is a figure that maybe Chinshu showed as well. So what's plotted here is the age of the star against the disk fraction. So this is the fraction of disk around the stars that still have a primordial nebular gas in it. So what this is telling you is effectively as the age of the star increases, there is a lower and lower probability of having the nebular gas in there. And effectively by about 10 to 12 million years, we don't see these primordial gas disks around the stars. So after about 10 million years, the gas basically dissipates away completely. And that the median time scale here is about 2.5 million years, which means that roughly half of the stars that are 2.5 million years old have nebular gas around them, and the other half have already lost the gas. So in effect, the picture that you are seeing here is probably on the order of 1 to up to 10 times 10 to the 6 years. Okay. And so now to the question of how rapidly do you grow these embryos? So is it feasible that embryos can capture nebular gas? And that's a question we can't directly address. We can only have a probabilistic approach towards this, because we actually, for our own star, we actually do not know when the nebular gas was dissipated. So this is a paper from Nicolas Dafoe talking about the accretion timescale of Mars. And
Sorry, I think there's lots to be learned still from that last point of discussion.
Sure.
Because just go back to this image.
It isn't, yeah.
It influences us so much. But Simon, take the opportunity, if I may. How did the disk clear out? Did it get thinner, or did it evaporate or accrete in some sort of radially different pattern?
Can I delay your question about 2 years?
This is important for everybody to have. You have that picture in your mind so often, but you do not know what it means to transition to a thinner or the absence thereof a nebula.
So this is complicated, and it's something that we don't agree on in a modeling context. The reason I asked to delay 2 years is because there is the ALMA telescope. That's a series of small telescopes that's hoping to be able to resolve down to a few AU structures. So we should be able to learn slightly more about the evolution of the inner parts of the disk, which we care about. At the moment, we can only really see that disks are there and get bulk properties, not individual properties. In terms of clearing, some people think that you have a front that clears backwards out, pushed by radiation pressure. This can be episodic. You can have a forcing away of material bursting out, being ejected from the midplane, and then returning, although no one agrees on anything. Or people think you have a combination, or the other extreme is you have a complete thinning. You just end up slowly stripping material off the top of the disk, thinning in all areas, and then eventually it's thin enough that it's optically thin and you can just drive escape. And you have combinations of both those models. It's just not.
Yeah, I think it's fair to say we don't quite understand how the disk gets cleared out. Okay, so this is a figure showing the accretion rate of Mars, and this is based on tungsten isotope that Jinshu In talked a little bit about. And the idea is that Mars's mantle has a slight excess in terms of the isotopic composition, which allows you to figure out how rapidly core formation happened on Mars. And based on that, Dafoe and Portman are calculating how rapidly Mars must have grown as a function of time. And so in red is their accretion timescale for Mars, and the yellow is showing the 95% confidence limit. And the two parameters that are going into this is basically the hafnium-tungsten ratio of Mars and the tungsten isotopic composition of the Martian mantle. And then in black shows you the timescale for growing something the size of Mars based on Nbody simulations at about 3.2 AU and at about 1 AU. So in effect, what this might mean is that Mars's accretion timescale is on the order of about 2 million years. And if we just go back one slide, so that would put us around there, which would mean that there is a high probability that the nebular gas had not yet dissipated. So again, remember, we can't know for sure whether the gas had dissipated or not, but by looking at other stars, we would say there's a high probability that the gas was still there. So there's a high probability that Mars-sized embryos might have captured nebular gases.
Going back to the Dafoe's figure, the growth of Mars figure, what does time equals 0 really mean?
Okay, so that's a
in this
good question.
case?
So in most of the cases, time equal to 0 corresponds to the condensation of the first solids in the solar system, which correspond to these calcium aluminum inclusions. And they've been dated to about 4.568 billion years, I think, at this point. So that's what time 0 is. It's the condensation of the first solids. Because you can't really date when the molecular cloud collapses, but you can date something that's more specific, like when the first solids came out of the gas.
I guess a related question, we're talking about a short-lived radioactive isotope here, which doesn't stay around very long. So
That's right.
Where did it come from?
So that's a great question. So the molecular cloud would have been injected with supernovas over a duration of time. And you can calculate the rate at which something like hafnium is decaying, and you can compare it with how much input there must be happening into the molecular cloud associated with supernova, because some of these isotopes have to be produced by supernovas. And I think you can show that for most of these short-lived radioactive nuclides, the molecular cloud must have been in steady state, meaning that what we are measuring in the initial solar system did not come from one single stellar explosion. The exception to that might be aluminum-26, which may not have been in steady state. But things like plutonium and uranium and iodine and hafnium seem pretty close to being in steady state, which means there were multiple supernova that contributed to the molecular cloud. Okay, so that's the first source of volatiles to planetesimals and planetary embryo, which is the solar gas. The second source of volatiles are chondritic volatiles. So that's very similar to what we find in chondritic meteorites, which today originate from the asteroid belt. And you can deliver those through small impactors, kilometers to tens of kilometers, maybe up to 100-kilometer size impactors. And it's even conceivable that a planet like Earth might have acquired some of those chondritic volatiles through things like giant impacts. It's important to keep in mind that not all giant impacts will lead to loss of volatiles. Giant impacts can also actually add volatiles. The other important thing, and I'll point this out later on, is that these chondritic volatiles have a different fingerprint in terms of their isotopic composition. So they have different isotopic composition of water, carbon, and noble gases. And then the third possible source might be icy planetesimals, which might have been scattered in from the outer solar system. And here's this is, I think, the comet Hale-Bopp. And the comets may be originating either from basically the Kuiper belt up here, or today they're coming in maybe from much further out. These are the long period comets coming in from the Oort cloud. So this is long period comets. Today the short period comets are coming in from here. But while accretion was going on, it's possible that there were icy planetesimals in this region that were being scattered in. And again, when we look at the composition of some of these comets today, they seem to have a slightly different fingerprint, again, in terms of nitrogen and water, when we compare it to carbonaceous chondrites and other chondritic meteorites.
Why is there
Why is there
dwarf
a
on your
brown
figure?
dwarf there? I'm not quite sure.
Bizarre.
It's not really important, but there's a suggestion in terms of perturbing the Oort cloud from a body in between Pluto and the Oort cloud, and people think anything. But if it was a brown dwarf, we probably would have seen it. If it's a
Yes.
smaller planet, maybe not, but it's a long way out.
I would say ignore that. Okay, so those basically are the three potential sources that could have contributed: solar nebula, chondritic meteorites or chondritic bodies, and these icy planetesimals. And when we look at Nbody simulation of planet formation, and here's one example from Raymond et al. So you're starting off here. So the color scheme corresponds to, in this case, water. So this is dry, red is dry, blue is wet. So you effectively start the simulations in some sort of a ordered fashion where the inner part of the disk is dry. You have the more water-rich planetesimals in the outer part. And in effect, what you see as the simulation goes on, that material from the outer part of this disk starts getting scattered in, and likewise material from the inner part might be getting scattered out. Okay. So in effect, what this means is that the feeding zone of these terrestrial planets were not necessarily confined to where you find them today. That basically you are feeding from a very large area of the nebula. So there is no reason to believe that these planets would have gotten their volatiles from one single source. It's likely that multiple sources contributed to these terrestrial planets, and they contributed maybe at different times. So initially you might have gotten some amount of nebular volatiles, and then as accretion went on, you might be getting volatiles from these chondritic bodies. Okay.
Is that like a fixed Jupiter in that?
Yes.
Okay.
Yeah. In this case, so this is not the grand tax. So this is there's no migration of Jupiter in and out. Yeah. So yeah, that's Jupiter there.
In essence, also that's an oxygen gradient as opposed to a hydrogen gradient.
Yeah, so Bill's question was that's also an oxygen isotope gradient in addition to being a water gradient. And yes, that does seem to be valid based on, again, our studies of meteorites. Okay, so what are the possible processes that could actually lead to loss of volatiles from terrestrial planets? And the first one here is hydrodynamic escape. And this is a process that will produce mass fractionation of isotopes. So the residual atmosphere that will be left behind on the planet, the isotopes would be fractionated from the starting composition. And the basic idea is that you would be dumping deep UV into the high altitudes. And if you have a hydrogen-rich planet, the amount of energy that you're dumping into the planet might lead to very vigorous escape rates of hydrogen. And the hydrogen escape fluxes might be high enough that they're going to dominate an upward drag force on the minor constituents of the atmosphere. So the minor constituents of the atmosphere could be things like nitrogen, CO or CO2, noble gases, and so on. And depending upon how much energy you're putting in, you can lift species as high as xenon, which is more than 60 times heavier than hydrogen, out of the atmosphere. Okay. So this is, again, something that you might expect if you have a hydrogen-rich nebular atmosphere. And if, as we know that the amount of energy or the EUV energy that was coming out of the sun was much higher 4.5 billion years ago than sun, this would maybe almost be inescapable, that you would have this kind of a mechanism where the hydrogen escape flux would leave you with a residual atmosphere with severe mass fractionation. The example here I'm showing you is from Krypton isotopes. So one of the things to remember about this talk is I'm not really going to talk about radiogenic isotopes. So these are all isotopes that are primordial, by which I mean that they're produced in stars and they're not produced by radioactive decay of any other elements or isotopes. Okay. The y-axis here is basically the deviation of the Krypton isotope composition of the sample from a standard. The standard in this case is air in parts per thousand. Okay? And there are 6 isotopes. So the way to read this would be, for this composition, effectively what you're looking at would be the Krypton 78 to Krypton 84 of the sun divided by the Krypton 78 by Krypton 84 of air minus 1. Okay? And then all of these compositions would pass through 0 because this would be Krypton 84 over Krypton 84 of the sun. That's 1. And obviously Krypton 84 divided by Krypton 84 of air is 1. So 1 minus 1 would be 0. So that's why all of these compositions, when you normalize this way, would go through 0. So effectively, the atmospheric composition has to be along this straight line because that's your standard. And when you look at, for example, the sun's composition, the sun appears to be enriched in the light isotopes of Krypton compared to air, and it is depleted in the heavy isotope compared to air. So this is the kind of signature you might expect if the krypton that you're seeing in our terrestrial atmosphere is a mass fractionated residual atmosphere. So the idea is that initially Earth's atmosphere might have been very similar to the sun's composition, and then as you have this hydrodynamic escape and you start losing krypton, you will preferentially lose the lighter isotopes compared to the heavy isotopes, which means that compared to the sun, the Earth would be depleted in the light isotopes and would be enriched in the heavy isotopes. And so that's what you're seeing. Earth's atmosphere is depleted in the light isotopes compared to the sun, and it's enriched in the heavy isotope compared to the sun. Couple of other things to point out. So that's the sun's composition. This is the composition of Mars's atmosphere, right along the sun. You cannot distinguish the two. So sort of keep that in mind. And then this is the composition that we see in carbonaceous chondrites. So in addition to having the terrestrial atmosphere be derived from mass fractionation of a initial solar composition, you can also derive it by mixing chondritic and solar gases, by the way. Okay. So.
Just a quick curiosity question. Do we have difference in krypton isotope composition between, say, phase Q, phase B, phase A in chondrite, or is it just a mono composition, like
so
homogeneous
this
composition?
is the average composition of carbonaceous chondrites, which means if you take a carbonaceous chondrite and you grind it up and you measure it, that's what the composition would look like. Yeah.
Phase Q.
Okay, so geochemists like to give names. So most of the krypton, probably on order 80 to 90%, actually is trapped in some organic matter, which is called phase Q. And the reason why it's called phase Q is because it is poorly being described, which means we don't really have a good idea of the exact chemical composition of that organic matter. What we know is that it's organic matter, but it's very poorly described. And that's why it's given the name phase Q. I didn't coin it. Michael.
If Mars looks like the sun, does that mean Mars has not lost krypton?
That could potentially be one interpretation. So I'll try and synthesize some of this information in terms of what we think might be going on.
Is there any constraint on krypton on Venus?
No, unfortunately no. There's a very poor determination of the krypton abundance on Venus, but that's about it. But that's a good rationale for doing. The moon's atmosphere is it doesn't have an atmosphere.
Can I just go back to organic matter?
Mm-hmm.
Does that mean methane? I'm assuming we're not chondrites full of little green men.
No, so this is macromolecular organic matter. So there are multiple carbons, hydrogen, nitrogen.
Okay, thank you.
Yeah. So it's not CH4. That's why it's actually difficult to characterize it chemically.
So when you're talking about phase Q, you're not actually talking necessarily about a single phase. You're talking about a mixture.
No, that's exactly right. So phase Q might actually be composed of many different organic compounds. Yes. Laurent.
If he crosses over, it's okay.
And don't break your head.
Okay, but the chondrite is a solid phase. The others are atmosphere and solar wind. Do we know the krypton of the solid Mars? I mean, maybe the atmosphere is not coming from the interior of Mars. Maybe it's actually completely solar wind. Who knows?
Solar wind wouldn't be trapped today.
Okay, but what I mean is that it could be.
No, that's also a very good point. And again, I'll touch very briefly about this. The short answer is we don't actually know the interior composition of Krypton on Mars. Okay, but this is often taken as an evidence of hydrodynamic escape happening and being important for terrestrial planets. So I'm just showing you an example for Krypton. If you look at some of the other noble gases, It has also been argued that they show evidence for mass fractionation associated with hydrodynamic escape.
It's very naive. You're
That's
comparing kind of atmospheres of various bodies with the chondrites. How do you define the atmosphere of a chondrite?
So this is the So again, chondrites won't have atmosphere. So this is basically the krypton that's trapped in the meteorite. So it's trapped in some solid phase, and in this case, we think that solid phase is a organic matter, and that when the organic matter was somehow produced in the nebula, it trapped the gases associated with some degree of mass fractionation.
But you don't do this for the moon?
No. So for the moon, again, we have actually, in many respects, initially before the Genesis mission, the way we determined the sun's composition was by studying lunar soil, because it was continuously bombarded by solar wind. So yes, we would love to know the interior of the moon. Okay, so the second set of processes that could lead to lead to volatile loss are impacts. And you can think of impacts in sort of two different flavors, giant impacts and then planetesimal impacts. This is a question.
So you said the reason we can't get Krypton isotopes from the moon is because they're being bombarded by the sun. Why is that different for the meteorites? Because most of them that land here have been around our orbit for most of the time, right?
That's right. So when you look at a meteorite, the implantation depth of solar wind into material is actually on the order of few tens of nanometers. And when the meteorite goes through the atmosphere, you effectively will ablate most of the outer material. But you still have to worry that maybe a long time ago, it might have seen solar wind irradiation. But the isotopic compositions are different, and you can play these games to basically figure out what's sort of your chondritic krypton composition and what's the solar krypton composition. Okay, so in terms of impacts, you can think of two flavors, giant impacts and impacts associated with planetesimals, so small bodies. And I think previously we used to think that this was not an efficient mechanism. Planetesimal impacts are not an efficient mechanism for driving volatile loss. But that might be changing, and there is now a paper in Press in Icarus by Hilke Schlichten where she argues that impacts associated with small bodies on the order of tens of kilometers can actually be exceedingly efficient in terms of driving loss of volatiles. So again, keep that in mind when you often hear that the late veneer is bringing in all of the volatiles. It's actually not clear whether those kinds of impacts are going to be accretionally or whether they're actually going to erode the atmosphere. So the reason why I'm not going to talk too much about this was because I got this paper literally a month ago and I haven't had time to look at it. But that's the paper that has looked at it in detail. Yes, so she's arguing that planetesimals are very efficient, and yes, let's leave it at that. But the one that I did want to talk about are giant impacts, and the thing to remember about giant impacts is that this leads to bulk ejection of the atmosphere. So you're not going to have isotopic fractionation, but you may actually have an elemental fractionation, because these impacts are going to preferentially erode the atmosphere compared to an ocean. So for example, when you are looking at things like carbon, carbon today, about 2% of the terrestrial budget of carbon is in the atmosphere. And the ocean has about 98% of the carbon when you look at the atmosphere-ocean system. On the other hand, nitrogen is dominantly in the atmosphere. There's very little nitrogen in the ocean. So because the elements can distribute themselves differently between the atmosphere and the hydrosphere, the giant impacts have the ability to fractionate one element from the other. They won't necessarily fractionate, or they won't fractionate the isotopes, but they may fractionate the elements from each other. So things to keep in mind is that these giant impacts might preferentially lead to loss of noble gases and nitrogen over things like hydrogen, which would be present in the ocean, and carbon, which would again maybe dominantly be in the ocean.
Impacts can cause evaporation, vaporization, and
That's right.
that can lead to isotopic fractionation.
That could lead to isotopic fractionation, but most of the material will get reaccreted, especially for the ocean. It turns out it's very difficult to lose the oceans associated with giant impacts, and I'll show some results that Simon presented in the poster session. So yes, you might get incomplete vaporization, and that will lead to an isotopic fractionation, but if you reaccrete back the volatiles, you're not going to be left with that isotopic fractionation. But yes, if you lose it, then yeah.
Really small point. Is carbon still dominantly in the ocean if you've got like an early Earth atmosphere that's all carbon dioxide?
Ask us in 6 months. Is that a fair? Yeah. So these are again some plots that Simon showed. So the top plot shows the atmosphere loss fraction against the energy associated with these impacts. So this is the specific energy of the impacts, and I guess the way to think about it is that this is the total kinetic energy divided by the total mass, and then you adjust that based on things like the impact angles and the relative mass proportions of the target and impactor. And this shows the energy distribution of the objects, and that's based on looking at these Nbody simulations and calculating what energies these giant impacts would be happening at. This is an example of an old moon-forming giant impact event by Knopp 2004. These are these high angular impacts that have recently been proposed in terms of forming the moon. So they're about an order of magnitude more energetic than the canonical moon-forming impact event. The top panel shows you the amount of volatile loss, and this line shows you, I should say, atmosphere loss, and this line shows you the atmosphere loss if you had no ocean, and this shows you the amount of atmosphere loss if you had an ocean. And in this case, the ocean to atmosphere mass is about 1:300. Okay. So one of the things you notice is that in the absence, for the same impact energy, in the absence of an ocean, you get very little volatile loss. And in the presence of an ocean, you might start losing some amount of atmosphere. And that's related to the impedance contrast between rock and water. So water is much more compressible than rock, so the particle velocity associated with the shock waves are going to be much higher in water than in the rock. And as a result, when the atmosphere is in contact with the ocean, it's going to get a much bigger kick than if it were in contact with rock. And so in the presence of an ocean, you would end up losing more of the atmosphere than in the absence of the ocean. And these different colors are related to looking at things like varying impact angles and varying the relative mass proportions of the target and impactor. And in case of the canonical moon-forming impact event, notice that you're losing something like maybe 20% of the atmosphere, meaning 80% is being retained. Okay, so there is very little volatile loss, actually. In case of these higher energy impact events, you might be reaching now 60, maybe up to 70% of atmosphere loss.
Can you somehow lose halogens and explain maybe their weird depletion in the mantle with this kind of process?
So in a paper that we just published, we argued that indeed the reason why, for example, chlorine is depleted with respect to fluorine is a signature of this impact, of this loss. But I'm not going to be talking about halogens today. Yeah, but we argued that yes. And then this figure shows you basically the proportion of ocean that's retained divided by the atmosphere that's retained. So for example, if you preferentially, let's say, lost the ocean, then this number would be less than 1. And what you notice, obviously, that everything is 1 or greater. And effectively what this means is that you're preferentially losing the atmosphere over the ocean, which kind of makes sense. And then again, if you remember, this sort of was the range of the most likely energy that would be associated with the impact, so somewhere between, say, 10 to the 5 and 10 to the 7. So somewhere between here and there. And you can lose something like most of the atmosphere with very little ocean loss. So the take-home point might be that if you had water on the planet, and if that water, or if you had hydrogen on the planet, and if that hydrogen was present as a water ocean, chances are you would not have lost that ocean. So we often think, or we often maybe used to think, that giant impacts would lead to volatile loss. And therefore, we had to get all of the volatiles after these very energetic events happened. But I don't think that's true. Actually, it's turning out that it's very difficult to lose volatiles with giant impacts. And again, remember that if you're preferentially losing the atmosphere over the ocean, you're going to be preferentially losing nitrogen and noble gases compared to maybe things like hydrogen and carbon, but not producing any isotopic fractionation. Okay, so those are the two main mechanisms through which you can sculpt the volatile budgets. And then the next thing to look at is when could these volatiles have been delivered? And the easiest way to think about it is that there are two end-member cases. One is that this is happening during the main phase of accretion, that all of the volatiles are coming in during the main phase of accretion. And by that I'm meaning it's coming in pre-moon forming giant impact. So any little bit of material that's added after the last giant impact is not bringing volatiles in. And again, these giant impacts could be erosive depending upon the exact energy associated with those impacts, or they could also be accretionary. The other end-member scenario is to say that all of these volatiles came in after the last giant impacts, so associated with a late veneer. And you can obviously think that there is sort of a continuum between these two. So most of the volatiles could have come in during the main phase, a little bit added after the last giant impacts. And then you can construct more complicated scenarios where even if most of it is coming in during the main phase, it may be concentrated towards the end of the main phase of accretion, meaning the initial part is quite dry and then it becomes progressively wetter later on.
I think now you're parsing your words volatiles. And I think when you're talking in this sense, you really are dividing up at some level, I don't know, chlorine versus carbon, hydrogen, nitrogen. I'd like to get a sense.
So what I'm talking here is still hydrogen, carbon, nitrogen, noble gases. So I'm not talking about halogens, and I'm not talking about potassium or lead or any other element that one might call volatile. Yeah. So as I said, this is only about hydrogen, carbon, nitrogen, and noble gases. Okay, so that's what you can go about in terms of addressing things like what could the sources have been, what could have sculpted the volatile sources, and when these could have been delivered. So now let's talk about how one might go about establishing the volatile inventories on the different terrestrial planets. So the first is Venus. And the way we know about Venus's composition is through basically the Venera missions associated with the Russians and the Pioneer mission, which was a NASA mission in the late 70s. So this is the lander associated with Venera 13, which survived on the surface for about a couple hours. And this is a mass spectrometer which measured the noble gas and hydrogen, carbon, nitrogen composition as it descended through the atmosphere. And here what you see are 4 probes being deployed into the atmosphere. This one was, the big one was the one that had a parachute on it with a mass spectrometer. So this idea was to slow it down so that, again, as it descended through the atmosphere, you would measure the composition. But these were not designed to actually survive on the surface of the planet for any length of time. So what this really means is that for Venus, we have a crude estimate of the atmospheric composition. We have almost no idea, or we have no idea of the interior composition of Venus. For Mars, we can rely on a combination of missions. So the surface compositions and inventories could be established or have been established by missions like Viking, Odyssey, MSL. So that's Viking there. That's the Curiosity rover associated with the Mars Science Lab. If you ever wondered there were people on Mars, that's the evidence. Somebody must have taken the pictures and sent it back to us. And then the other very important piece of evidence that we have about learning about Mars are these Martian meteorites. So just a quick note on how we really know for sure that these Martian meteorites come from Mars, and I think Anat briefly alluded to it. So in the bottom figure is an experiment that was done in the Johnson Space Center. So what they did was they ended up shocking a basalt, and they studied the gas composition in the basalt as a function of the composition of the ambient atmosphere. So these are all the different species of gases, and effectively the concentration of those species in the shocked basalt lie on this 1-to-1 line with respect to their inventory in the atmosphere. So what this is telling you is that the shock implantation of atmosphere into the basalt is not fractionating one species from the other. And that's very important if you want to try and reconstruct what the Martian atmosphere would look like, because you have to make sure that you haven't fractionated one element from the other. And then this is an example from the EETA meteorite from Mars, where again you see these different species in the meteorite plotting on this 1-to-1 line with what was determined by Viking. And so these two experiments basically establish that these meteorites are indeed originating from Mars. Okay, so for Mars then, we rely on these missions and on the Martian meteorites to tell us about both the surface and the interior.
Do we know how those pieces got here?
They were ejected by impacts from the Martian surface. And I think in the early 1980s, there were I don't think physicists had yet figured out how to do it, and so they were adamant that you could not get meteorites from Mars. But these are associated with ejections of meteorites. And it turns out, based on some paleomagnetic work that Ben Weiss's group has done at MIT, that the temperatures that these meteorites are subject to are actually fairly low. Some of them might only be heated to things like 40, 50 degrees during the ejection. Go ahead.
This can be a really naive question. So you had said that the implantation of these noble gases by the atmosphere goes down to about a few nanometers or so. So for the Martian meteorites, when they enter the Earth's atmosphere, wouldn't they have these outer rines eroded or something? So how do they still preserve the implanted signatures?
So this is shock implantation. That's different than solar wind irradiation.
Okay, so the depth
so this is
much
yeah, that's right.
higher.
Yeah, and
okay.
this is not just true for the noble gases. So here, I don't think you can actually read it. So that's nitrogen, that's CO2.
Okay.
Yeah. What is the age of the meteorites, of Martian meteorites? I mean, does it represent the composition of Mars right now or in the earlier Mars?
So that's a great question again. We have some meteorites from Mars that we think date back all the way to 4 billion years. And then there are meteorites that are 2 billion years, like the Knocklights and maybe Chisigny. And then the Shergottites are younger, maybe on the order of a few hundred to maybe 500 million years old. So yes, there is a age spectrum that the Martian meteorites cover.
Do you see the changes of composition?
Yes, it has actually been argued that you see a change in composition associated with things like argon. Yes. Okay. That 4 billion years ago, the argon isotope composition on Mars looked much closer to solar or chondritic values compared to what you see today. And 4 billion years is roughly when the magnetic field disappeared. So this idea of solar wind sputtering of the atmosphere in the absence of the magnetic field has then subsequently led to loss of argon-36 from the planet. Yeah, so we think we actually see that change.
Okay, but the gas that is seen from in the meteorites from that graph that you have there is shock. It's a shock emplacement, so
That's
that
right.
the atmosphere when the meteorites were shocked and ejected, not when the igneous rocks formed.
That's
so
right.
that may not be the 4 billion years old atmosphere, but 200 million or whenever it was that it came out.
So ALH 84001, which is in many respects a notorious meteorite, actually has some evidence that it underwent a shock event at about 4 billion years. So this is a orthopyroxenite which shouldn't be present at the surface. So we think that it went through at least 2 of these shock events, one which excavated it from deeper in the mantle to the surface, and then the second one launched it from the surface. So with the first one, we think that impact happened at about 4 billion years. So there are lots of carbonate blebs that have been dated that go back to about 4 billion years. So it's possible that that's when you implanted the atmosphere into those sedimentary material in the meteorite. Apparently not. Okay, so how about Earth's composition? So this should be relatively easy, right? We have lots and lots of samples from Earth. But as these pictures suggest, it's actually quite difficult to establish the total budget of volatiles on Earth. And here's an example of a vesicular basalt. So what you see are all the gas bubbles here, except the gas is not there. This is an example of a popping glass. So these are exceedingly gas-rich basalts. When you bring them up to the surface, they pretty much start exploding because they're overpressurized. So they're a delight to work with because you can handle them with your bare hands and have glass shards flying everywhere. But again, what it means is that it's very difficult sometimes to get at the total amount of hydrogen, carbon, nitrogen, noble gases through a simple measurement of these basalts. You have to then figure out the amount of degassing that has happened to go back and talk about the mantle budgets. And so what I'll do in the next few minutes is talk about how one goes about establishing these budgets. So here is one example. This is a paper from Bernard Marty in 1995, looking at the carbon-nitrogen ratio and the nitrogen-argon ratio against the helium-argon ratio. And there's actually a good reason why geochemists like ratio plots, because of the fact, again, that getting at absolute abundances and absolute amounts is incredibly difficult. There are lots and lots of processes that can change the absolute abundances. Ratios are more difficult to perturb, and isotopic ratios are even harder to perturb. Okay? So helium-4 is produced by decay of uranium and thorium, and argon-40 is produced by decay of potassium-40. So this ratio of helium to argon can actually be used as an indicator of the amount of degassing that a piece of basalt might suffer. Because we think we have some constraint on the uranium to potassium ratio of the mantle, we may not know the absolute amounts of uranium and the absolute amounts of potassium in the mantle, but we think we know the uranium-potassium ratio. And if you know the uranium-potassium ratio, you can calculate what this ratio should be in the mantle. And that's what's shown by this gray bar. It should be in this range of roughly 2 to 5. So if you get a piece of basalt with a helium-argon ratio of between 2 and 5, you can be fairly confident that that basalt has not been subject to severe amounts of degassing. Okay? So the idea is as you degas a basalt, helium ends up being much more soluble than argon, so you would preferentially lose argon. So you lose this compared to helium, which means that the residual gas ends up having high helium to argon ratio. So that's why as you degas a basalt, you make this go to the right. So on the top panel, what you see is a relation between carbon-nitrogen ratio in the basalt and helium-argon ratio in the basalt. And what you can say is, based on this correlation, I can just read off what the carbon-nitrogen ratio of the mantle is given this helium-argon ratio. And that's actually how we establish the carbon-nitrogen ratio of the mantle. On the bottom panel, what you see is the nitrogen-argon ratio as a function of degassing. And in this paper, they argued that this was effectively constant, that the nitrogen-argon ratio in the basalt is not changing as a function of degassing. And there is actually some reason to believe why that may be the case. These two species end up having very similar solubilities in a basalt. So even if you degas it, you are changing the total amount of nitrogen and you're changing the total amount of argon in the basalt, but you're not changing their ratio. The ratio is remaining roughly constant. So if you have a whole bunch of measurements, you can take the average, and that gives you the nitrogen-argon ratio of the mantle. So again, this is a way whereby you can establish the relative abundance of one element compared to the other. This is not telling you about the absolute abundances. So how do we go with this? Is the oh. Okay, so what I'm going to do is I'm going to give you sort of how people have done this based on two recent studies, one by Bernard Marty and one by Alex Halliday. Okay, so the first one is by Marty. This is in 2012. And so what he did was he took a potassium content of 280, Bill is going to like this number, plus minus 60 ppm in the Earth. Okay? So remember this number. Everything that he's going to calculate is going to ultimately be tied to the potassium content of the Earth. Okay? So if you know the potassium content of the Earth, you can calculate how much argon-40 is being produced. You know how much argon-40 is in the atmosphere. And then by mass balance, you can calculate the amount of argon-40 that's in the mantle. Not necessarily in the upper or lower mantle, but just in the whole mantle.
Sujoy,
yes.
I just say that 280 number was put forth by a 2008 CIDERite. Yes,
so this comes from Aravalo and McDonough, which is why I said Bill is going to like the number. It's a CIDERite, yes. There are obviously alternate ideas of what this potassium content is. A lot of people, like, for example, Matt Jackson, would argue this number is quite a bit lower, maybe like 180 ppm or so. Okay. But effectively, the uncertainty in the volatile abundance that Bernard Marty calculates, it's tied to the amount of potassium to a certain extent. Okay? So if you know how much argon-40 has been produced over its history, you know how much is in the mantle, how much is in the atmosphere, you could calculate how much is in the mantle. And then you get the nitrogen abundance. So this is nitrogen in mantle, argon-40 in the mantle, multiplied by and I just showed you in the figure below how the nitrogen-argon ratio was determined. So this tells you the nitrogen in the mantle. So when you know that, you can find the carbon from the carbon-nitrogen ratio, which again I showed you how we established. Just keep remembering that you have to propagate your errors every time.
Sujoy, the plot you showed us of the carbon-nitrogen ratio had a huge amount of scatter. And if there hadn't been a straight line, which I guess you called a solubility prediction, only a geochemist would have said there was a pattern.
Right there. That is a log plot. So, yes. But that's how it's done. So that's why I'm saying establishing absolute amounts is a challenge. And let's just see what the difference is in two slightly different approaches. Okay. So the hydrogen budget then comes from taking this carbon budget and multiplying it by the hydrogen-carbon ratio, which was established by Hirschman and Dasgupta. In 2009, I think. And the value they had was about 0.75. Okay, so when you do this, effectively what it implies is something like 2,700 plus minus 1,350 parts per million water in the mantle. Does anybody have a feel for whether this is high or low, or? Just to sort of point out that even most OIBs don't reach this value. So we think of OIBs as maybe having more water than mid-ocean ridge basalts. Most of them would indicate water contents in the source that's up to about 1,000 ppm. So if this number is right, then it means that there must be a part of the mantle that we are not sampling through volcanism.
I'm just curious, if you, instead of distributing that figure homogeneously throughout the whole mantle, if you stuff it all in the transition zone, does it saturate or oversaturate the transition zone?
I don't know.
Yeah.
So then you would have, yeah, you could do that calculation, I guess, yes.
That could be another constraint.
Yeah.
If that oversaturates what we think the highest, the soggiest part of the mantle is, then.
But that would mean that you're not against sampling that through
Right.
volcanism.
Right.
Just, yeah. So there's some kind of water filter then in the mantle.
Okay, Sujoy, so you said because we don't observe 2,700 ppm water in even the, I guess, most water OIBs, that means that the rest might be in the mantle. What about the core?
No, because this is coming from the amount of potassium in the bulk silicate earth. Then you can calculate how much potassium is in the core, but this is basically bulk silicate earth potassium.
Okay, so if there's no, I'm sorry, I didn't understand that.
So this is in the silicate, so this amount of potassium is in the silicate part of the earth.
But there's no reason that the water couldn't be in, right? Does the water have to go with the potassium? Well, essentially, what you're saying is that if that's
yes,
the bulk
because
silicate.
all of these ratios are being determined for the mantle, right? So the argon-nitrogen ratio was for the mantle, the carbon-nitrogen ratio was for the mantle, the hydrogen-carbon ratio is for the mantle.
Yes, but some of the water from the mantle might have gone into the core, and it would have left the potassium in the mantle, wouldn't have affected that, right? Am I thinking incorrectly here? I don't think so.
But wouldn't that mean that it would be even higher if you had something in the core?
I
think you are not understanding that the initial number comes just from the mantle. So if hidden some in the core, then your estimates of H would even be higher than 2,700 ppm.
That's bulk silicate Earth should actually have a higher potassium.
That's right.
And so that propagates.
Yes. So these are all numbers in the mantle. So, and it's in the present day mantle.
You make it in the mantle, then you push only the water in the core.
But then you would change your hydrogen-carbon ratio, right?
No, he's okay. The bottom line is, you're right, he's right. He's thinking about what happened a long time ago. You're thinking about the instantaneous Earth.
That's right, but this is the amount in the instantaneous Earth.
Right, that's all we can say right now.
That's
how
much water
you could have been
is.
right.
Yeah.
And there can be a heck of a lot of hydrogen in the core today.
Yeah.
But it all happened before we even had these measurements.
And in which case this would be even higher. Remember, this would be even higher.
Correct.
That's right.
So that saying that that's high, doesn't make sense with his expectation. He can't make sense of that high because of his expectation.
I see.
That's right.
Because
Right. That's right.
He's actually making it more complicated because he's talking about a bulk Earth hydrogen content.
Okay, so the way to think. Sure.
Can we distinguish which of these numbers are for the bulk silicate Earth versus which of these are for the volcanically observable part of the bulk silicate Earth?
So I think that's a great question. So this is all for what we think is the volcanically observed part of the bulk silicate Earth, right? Because the potassium content is being derived by looking at lavas. The nitrogen-argon ratio is being determined based on looking at basalts. Same with carbon-nitrogen, same with hydrogen-carbon. So these are all being determined through basalt. So it's effectively what we are observing. So if you do that, then you're coming up with something like 2,700 ppm water. So this is the average over the mantle. So just something to keep in mind in terms of the high amounts of water.
Is that really fair error propagation? Because it seems like with the amount of multiplications of very uncertain quantities you've got there, I would have expected at least 100% error. At the 2 sigma level, it is.
I think, So that's. So I should put that this is 1 sigma. Yes.
Okay. So at 2 sigma, we allow no water and ridiculous amount of water.
Yes.
Okay.
Yes.
So these are all numbers for the whole mantle, but we don't see the whole mantle. They're all from basalts. So I think I'm missing a bit of logic somewhere. How does the H/C ratio reflect the whole mantle? The Hirschman and Discopter.
So the H/C is determined based on looking at mid-ocean ridge basalts and by looking at ocean island basalts. And if you say that that's effectively sampling all of the mantle, that there's nothing else being hidden.
So the explanation that was proposed a couple of minutes ago, that you could hide a load of hydrogen in the transition zone, that's not taken into account in this ratio.
I see what you're saying. Yeah. So I guess no, because it's all being determined based on what we are seeing today. Yes. Yeah. Yes. So it's high, right? It's a very.
So just a very, very small point. I think the story changes a little bit if we normalize water to cerium, so to incompatible lithophile elements that we know much better in terms of magmatic behavior and in terms of mantle abundance. And we don't see these crazy estimates like 2000 ppm or something like that. So
why is it crazy?
It's insane.
So you have to justify why it's insane, though.
I mean, when you normalize water to cerium, which has a very comparable magmatic behavior, you
So then you have
compared
to, again, that's a ratio, so somehow you have to get at the absolute abundance of water.
Yeah, but the uncertainty on the cerium abundance in every model for the mantle compared to the carbon is much, much, much lower. We know so much more in terms of study of mid-oceanic rich basalts and ocean island basalts. So the estimates that we got from this vary between 150 and 250, if I'm correct. So, I mean, the uncertainty is, I think, much lower.
Yeah, so let's look at a second estimate. So this is from Halliday's group.
Sorry to slow it down on this, but I actually certainly find the previous method to be totally inconsistent, because you are using ratios that have been determined on basalts and OIBs to get an estimate of water, hydrogen, and then you tell me that the OIBs don't have enough water, don't have enough hydrogen. I mean, that's the same rock type, so it means the circle of elements is inconsistent some way or another. I mean, you see, all of the constraints were coming from basalts, and eventually you got an estimate of H which doesn't work with the measurements on the basalts. So somewhere there's a step that's missing, or that's all in the errors, right? Because you said eventually there's not enough water in even the most wet OIBs. So the system is not close somewhere or not. I mean, because you end up having two independent estimates of hydrogen on the same basalts, one through using all of these circles of ratios, and one from directly measuring it. Because at the end you told us that there's some measurements that have been done on this, and they are incompatible.
So hold your thoughts. So this is the other estimate by Halliday. So what he says is the Morb average is about 2,000 ppm. And remember, Morb is a melt. Okay? So this is Morb average water is 2,000 ppm. So the average content in the melt is 2,000. So you have to figure out what's in the source. And if you look at, if you assume that it's about a 10% partial melt, and with any reasonable estimate of D, this would imply about 200 ppm water in the source. I think you have to keep in mind that the two different methods of doing this give you two very different results, and maybe have, well, okay, let's just see what we get.
That going from 2,000 to 200 assumes that water is like 100% incapacity.
Effectively, yeah, but it's not a bad assumption. The D values are about 0.01, so you would be very, very close to 200 ppm. Okay, so when you look at a place like Hawaii, the Hawaiian source would give you something like 400, maybe plus or minus 30 ppm water. Okay. Now there are some OIBs where the source will go up to about 1,000 ppm. But what Halliday does, he basically says is, well, I think this is a good enough estimate for OIBs, and so the average mantle value he takes as 300 plus or minus 100. Okay?
To assume some source volumes then, right? He has to assume how much of the mantle the Hawaii source is and how much of the mantle the Morb source is.
So if the Morb source is the whole mantle, you get something like 200.
Right.
And he says, well, that's within the error. And if the whole mantle looks like Hawaii, that's 400. So that gives you the sense of how, the estimates, right? And that's why this is not an easy thing to do. That's why absolute abundances are incredibly difficult. Okay, so once you know the water content, then you play the same game. Carbon is this is again from Hirschman and Dasgupta. Nitrogen is basically And this is from Marty's 95 paper and so on. Okay? So that's effectively how these abundances get established.
That's also for the CO2 helium ratios.
For the noble gases, yeah. Okay, so let's look at these two different estimates in terms of what you get. There's a lot of numbers. They're not necessarily going to mean anything. So these, one thing to keep in mind is they often get normalized to 10 to the 6 atoms of silicon, simply to take into account the different sizes of the planets. So if you want to compare Earth to Mars, you have to factor in the mass as well. And they're reported in terms of hydrogen, carbon, so on. So effectively, this amount of hydrogen that Marty calculates ends up approximating something like 10 plus or minus 5 oceans. And the amount of water that Alex Halliday calculates ends up being something like 1.7 plus minus 0.3 oceans on the Earth, which would mean that since you have one ocean on the surface, you have about 0.7 plus minus 3 oceans in the mantle. Whereas in this case, you may have somewhere between 4 to 14 oceans in the mantle. So this is a fairly big uncertainty. And the way I sort of think about it is that these two estimates are probably bracketing the range of the true volatile abundances. And that this is an uncertainty that's probably on the order of between factor of 5 and factor of 8.
Sujoy, but this would make a huge difference, right, to both possibility of partial melt and dynamics?
Yes, there's no doubt about it. But I think it's an illustration of why it is very difficult to get at absolute amounts. That I think the elemental ratio is better than the absolute amounts. So if you look at the elemental ratios of these different species, both estimates end up being very similar in the ratios, but the absolute amounts end up being very difficult.
Sujoy, just to clarify, you said that 1.7 would mean there's only 0.7 in the mantle, but I thought these numbers were all coming from mantle, from glasses. So this is 1.7.
And then you add in all the surface inventory. So this is, for example, this column is the mantle inventory, and this column is the
that's coming
total.
from that column. Great.
Yeah. It includes, yeah. So again, Earth's mantle, Earth's total, Earth's mantle, Earth's total. Okay?
I just wanted to point out, you said that the...
Is it green?
I wanted to point out that you said that the ratios are pretty similar, but that's not surprising since they're based on the same ratios.
Yes, in some cases, but not always. So for example, Halliday does not use the nitrogen-argon ratio.
Okay.
And he uses different ways of getting at the noble gas abundances than Marty does. So the only common ratio they use is hydrogen-carbon and carbon-nitrogen. Okay.
So
this is just for reference, again, just to show you the different abundances or to list the different abundances. This is Alex Halliday's abundance of what's on the Earth, and this is comparing it to the Venus atmosphere, Mars atmosphere, solar carbonaceous chondrites, comets, so on. So let's look at, for example, a plot like this, which shows you, in this case, the noble gas abundances. Let's not worry about xenon for the time being. And what this is normalized to is, for example, this would be neon in the Earth divided by the amount of silicon in the Earth, neon in the Sun divided by the amount of silicon in the Sun. So again, that's why the Sun's composition is on the flat line. This is the composition of Mars, Earth, Venus, chondrites. So when you look at this, what are the couple of conclusions you may draw? So does the Earth look like the Sun? Right? So basically, you could say that we are not seeing a solar composition here, right? The overall pattern seemed to be like meteorites. And then when you start comparing the planets, what do you see? Yeah, so Mars' trend is similar to the Earth's trend, is similar to Venus, which is similar to chondrites. But Venus has the highest abundance of noble gases compared to Earth and Mars. So it's got about 20 times more neon, and it's got about 70 times more argon. So those are huge. And in terms of thinking about, the acquisition of volatile, it's not a trivial question to answer. Like, why did the inner planet get so much more noble gases compared to Earth?
That's just in the atmosphere, right? The Venusian atmosphere?
That's just in the Venusian atmosphere. We're not adding anything in the mantle.
So that's Venus atmosphere, that's in the Earth atmosphere and Mars atmosphere?
That's a great question. So this was Venus atmosphere, this is Mars atmosphere, this is Earth's atmosphere. Actually, it's not true. It's bulk Earth. Okay? So let's add nitrogen and carbon in the play, and let's come back to your question about atmosphere versus mantle. So again, Mars, I'm not plotting, Mars, Earth is the red points, purple is Venus, and the CI chondrites are in black. So again, this is showing you Venus is much more enriched in the noble gases. When you start looking at nitrogen and carbon, it almost flips around. So for example, when you look at carbon, Earth is more enriched in carbon compared to Venus. And Venus might be a little more enriched than Earth in nitrogen. Okay, so that's again a kind of a puzzle, right? Why so much higher noble gas abundances?
Quick question: are there uncertainties on these values, or because it's making orders?
I think I gave you the uncertainties, right? You go back. You can make these plots yourself, right? They're the uncertainties. 1.7 plus or minus 0.3. One thing to keep in mind is that this is a log scale. Okay. Yeah, this is a log scale. So it is kind of very difficult to get at the total budgets of carbon and nitrogen. If you thought getting the total budgets of carbon and nitrogen on Earth was hard, there's no way you can get the total budgets for carbon and nitrogen on Venus. And this actually, the way these are plotted, is this is bulk Earth, not atmosphere of Earth. And the reason why this might be important is if you look at this column, for example. So when you compare noble gases, these are the two different models, Marty versus Halliday. This is the amount, or this is the percent of the species that's in the mantle. So in this case, the noble gases are between 15 and 14%. The rest is in the atmosphere. And in Halliday's model, it's between 0.6 and about 1%, or 0.2 and 1%. So a few percent of the noble gases are in the mantle. Everything else is in the atmosphere. Now, if you start comparing hydrogen, carbon, nitrogen, that changes. So for carbon, it could be somewhere between 99 and 67% in the mantle, meaning the mantle is the dominant reservoir, not the atmosphere.
Yeah, this is also maybe kind of a silly question, but Earth obviously is covered in things that are alive. So if you, do these measurements just, because we like take the carbon out of the atmosphere to
So
live,
this is
right?
it takes the carbon in the exosphere.
Is
so
that
not
significant? Are we like a significant reservoir of carbon compared to the atmosphere, or is it like negligible?
We are not significant compared to what's in the oceans and what's in the in sediments.
But what's in the ocean is biologically.
Yes, but that's not us. Right?
Okay.
So yes, most of the carbon is in the oceans and in the sediments. Bill.
I think this is worth pointing out. When you talk about X% in the atmosphere, such as 90, 99, 51, my eyes focused immediately at argon-36 and saw that there's only 5% argon-36 in the mantle. That's in the mantle?
That's in the mantle.
Right, and approximately 0.2 in the mantle. That instantly tells me that these people are both asserting that the transport of these gases to the mantle happened early.
Or that it's not being transported to the mantle efficiently.
Right.
I don't think it's an assertion, by the way.
I bet it's not an assertion, but it's a requirement as a result of their numbers.
Yes. Let's explain that in a little bit. So I'm almost halfway through my talk. So if you just start comparing the atmospheres of the three different planets, you still, I think, have a problem where the noble gases on Venus are significantly enriched in neon and argon compared to Earth. Carbon and nitrogen now in the Venusian atmosphere is higher than what you have in the terrestrial exosphere by about a factor of 2 to 3. So you could still argue that Venus is overall richer in all of the volatiles, with the exception of water, of course, which it has lost. But with respect to carbon, nitrogen, and noble gases, there's more of these on Venus than on Earth, at least when you look at the atmosphere. But it's very difficult to figure out overall whether Venus as a planet has more because we don't have access to the mantle. And sort of the same is true with Mars. We can't really go after the Martian volatiles. So I'm going to take a few more minutes just to illustrate a couple of points. So overall, when you look at the relative abundances of the elements, as I said, they don't look like the sun, right? They look very much like the carbonaceous chondrites. But when you start looking at the isotopes, you may start getting a slightly different view. So these are all these ratio plots again. There's no radioactive decay. Another thing to keep in mind is in these ratio plots, when the denominator is the same, two-component mixing will effectively give you a straight line. Okay. So what you're seeing is the sun's composition down here in neon isotopes. This is argon-neon ratio. The atmosphere is here. This is effectively the range in neon isotope composition of CI chondrites. The upper mantle plots somewhere down here. And this is the deep mantle that we determined for the Iceland plume. So in terms of the isotopic composition of neon, the mantle at least looks very much like the sun. The mantle does not look like chondrites, even though the absolute abundance pattern tells you it looks like chondrites. So the mantle is telling you something fundamentally different than what the atmosphere is telling you. And so there is one option, which is the way you generate the atmosphere is by undergoing this kind of a hydrodynamic escape. So you outgas the mantle, and then you lose most of the neon. So that's one potential. So you can try doing that, except what you find is that the evolution, the mass fractionation line takes you this way, if you start with the solar composition, like what we see in the mantle. So it's very hard to get to the atmospheric composition. And the idea here is that maybe the atmospheric composition could be explained effectively as a mixture of chondritic material and solar material. And that the Earth as a whole, when you look at the deepest part of the mantle, you might be getting some of these solar noble gas signatures. As you get to shallower mantles, you might start to see more of the chondritic volatiles. And then when you're at the surface, you start really seeing the chondritic volatiles. And in terms of argon isotopes, again, not plotted here, but argon in the atmosphere looks exactly like what you see in meteorites, not like what you see in the sun. So again, there is some evidence that the deep mantle got solar gases, but the atmosphere is recording delivery of chondritic gases. And in terms of the overall budget, it may not make a big deal because this is 90% of the budget. This is a few percent of the budget. So now let's look at the hydrogen and nitrogen composition. Again, the way to think about these is that these are fingerprints of what sources could have contributed to the Earth. So deuterium-hydrogen ratio, nitrogen 15 to nitrogen 14 ratio. This is the sun's composition. This is the Earth's composition. These are long-period comets, and here's a short-period comet. And the idea again here is that the Earth looks very much like what you see in meteorites. Does not look like the sun, does not look like comets, does not look like long-period comets, does not look like a short-period comets. Meaning that most of the carbon and nitrogen on our Earth must have come from these chondritic volatiles. Now this kind of a plot is not telling you when these gases or when these volatiles were delivered. They're just telling you there's a fingerprint of a chondritic delivery. So I'm going to stop very quickly, but maybe I'll show you this plot here, which shows you.
Just very briefly, Mars looks very much like comets. So is there
this Mars atmosphere. So this is because of loss from associated with solar wind sputtering. So Mars's interior is actually down here. Okay, it's displaced a little bit towards the sun's composition, as measured by the SNCs, exactly. So there is some, yeah.
So I have a question. So those data were collected at room temperature, right? So, but in real mental conditions, it's at high temperature. Will the temperature have any effect on the ratio?
You mean these ratios?
One slide before. Maybe. Yeah, those ratios. Yeah. I mean those isotope ratios.
Yeah. So these, notice that these are not being plotted in delta units. So this is an enormous difference. So there's effectively you're not going to see any kind of mass-dependent fractionation. The other thing to remember is that these are noble gases, so they're not going to be involved in any kind of bonds. So the degree of fractionation, if that's what you were asking, is effectively negligible. So this is indeed telling you about the composition of the mantle and so on. Okay, so let's just maybe end soon. Hydrogen-nitrogen ratios against the carbon-nitrogen ratio. So these are the different classes of enstatite chondrites. This is a CM chondrite, CI chondrite. So we think that in terms of the hydrogen-nitrogen isotopic composition, in terms of carbon isotopic composition, the Earth really looks like it should be there. But it doesn't matter whose inventory you take. It plots way off to the right when you look at hydrogen-nitrogen ratios. So there's been a number of studies, not just Bernard Marty and Alex Halliday, but other people have also estimated nitrogen abundances, and you always see the Earth ending up with a high hydrogen-nitrogen ratio. This is a factor of about 10 to 20 away from CI chondrites. So that's the uncertainty in this ratio is not a factor of 10 to 20.
Content is. Okay.
It is not a factor of 10 to 20. It's much smaller. Maybe you could argue it's a factor of 2 or so.
It depends on the speciation of nitrogen in the.
So the idea is that there must have been some process that affected this ratio. So what are the two processes you could imagine? One could be core formation, right? That maybe nitrogen went into the core. But if that's the case, then it's telling you something about when these volatiles must have come in. It's telling you that the volatile delivery must have happened before core formation was over. Because if you had delivered all of the hydrogen, nitrogen, carbon after core formation, you would not have led to this depletion of nitrogen. So you could then be arguing that this is happening as a result of core formation, but then volatiles are coming in before the last giant impact. Or you could argue that this might be a signature of an atmospheric loss event where the hydrogen in the ocean has been retained, but the nitrogen has been lost because the nitrogen is in the atmosphere. Again, in that case, what you're effectively arguing is that most of the volatiles must have come in before the last giant impact. Because if you just delivered volatiles of this composition after the last giant impact and after core formation was over, you would not end up at this point. So I think I'll end here with this talk.
So is the last giant impact here like the moon forming impact?
Yes, we think it's the moon forming giant impact. So this would mean that most of the water came in before the last giant impact or before the formation of the moon. And that would also help to explain why you see similar isotopic composition of water in the lunar mantle, which is what Alberto Saul and Eric Howry have been suggesting recently.
But if you take an early Earth atmosphere that's 98% carbon dioxide, and you strip that out, wouldn't that just affect your x-axis and not your y-axis quite so much?
Carbon dioxide?
Well, I'm just, you're saying we've removed nitrogen because we blew out the atmosphere, and the atmosphere has a lot of nitrogen in it, and all of the carbon and hydrogen's in the ocean, and we didn't get rid of the ocean. Am I stating that argument correctly?
Sure, yeah.
But presumably when this giant impact happened, we didn't have nitrogen, oxygen atmosphere.
You didn't have an oxygen atmosphere, for sure.
Yeah, we had.
But you had nitrogen in the atmosphere.
Yeah, sure. But I mean, it seems like most models of early Earth atmosphere I've seen are more like Martian abundances of carbon dioxide. So
Sure.
You're getting 98% carbon dioxide or something like that, or higher.
Mm-hmm. Yeah, so you would have lost some of that carbon as well, and
so I'm saying you wouldn't perturb the CN ratio very much.
You wouldn't. You would perturb the CN ratio. So that's a trickier thing to address because it would depend on how the carbon was partitioned between the atmosphere and the ocean. Because you could have, if you have a very acidic environment, then most of the carbon is in the atmosphere. But otherwise, you could have substantial amounts of carbon as bicarbonate and carbonate. So that's a trickier question. And Hirschman and Dasgupta have actually suggested that there was carbon loss because the hydrogen-carbon ratio on Earth is not chondritic. Louise?
Just to make sure I have a feel for the numbers, and on the plot of comparing Venus and Earth and so on, if you took the more extremely volatile-rich Earth, the 10 oceans in the mantle Earth, and pulled all those volatiles out of the bulk silicate Earth and put it into the atmosphere, how close would you get to Venus's atmospheric abundances?
So in terms of the noble gases, it wouldn't matter because most of them is in the atmosphere. Earth's carbon would effectively end up somewhere up there, and the nitrogen would end up somewhere up there.
So you can't just make Venus's atmosphere by dehydrating an Earth-like composition?
Nope.
That is the end of the program. Enjoy.